Hello everyone. Today I'm going to talk about technology similarity and bilateral trade in the semiconductor industry. This one especially we are using natural language processing with the deep learning process applying to international economics. So in other words, I can name it network evolution of technology embedded trade. Let's get it started. The main research question in this project is, does technological similarity between countries predict bilateral semiconductor trade flows beyond GDP and distance? So the idea starts from classical gravity model in the trade field. As an economist and specialized in the international trade, I'm dealing with so many times to run regression model of gravity model. So basically gravity model starts with the idea that Newtonian physics. The gravity is measured by the masses of two objects and divided by the distance of two objects. We all know that equation of physics. So that is a starting point. But when we measured in the trade gravity model, the gravity itself can be interpreted as trade volume. So total trade volume can be determined by two countries' masses and distance between two countries. So the masses can be interpreted as GDP in economics. So GDP of country of origin and GDP of destination countries and distance of two countries can be determined the trade volume. So it is working fine and well actually, starting from the trade volume data exists and so far. And behind the scene of it, trade volume can be explained or predict well by other aspects. So there is some other variable we want to add and try to explain that, there is some variable to affect to trade volumes. And by doing so, if it is significant in the regression model, we can suggest some policy. Connection with that gravity model, I try to put in the variable as technological similarity between the countries. So how we can measure that? Use natural language processing. So this project, we connect the semantic content of national patent portfolio and using that variable, predicting power of trade volume can be better or not is the main idea of a starting point. So this is what I have been doing to do that. So we learned the natural language processing, but the semantic content of national patent. So patent is similar to each other. We think that is technologically similar between two countries. So using the cosine similarity in the natural language model and apply that to gravity model, and we will see the result out of it. So first thing, as we learned, embedding is necessary to getting the cosine similarity. So pre-processing is done, embedding is done, put it in the model to get the corresponding vectors and calculate the cosine similarity and putting in the gravity model and then get the significance level out of that model is ultimate goal and results. I expect that country with more similar technological similarity trade more, and even we controlled all the gravity variables, we can get the same persistent results. So that is statistical hypothesis I want to testing out. Well, why do we see the semiconductor industry only? Well, I try to do in general or as a whole economy of patent data, but data itself is huge. Even though I pin down the semiconductor industry, my personal computing power is lacking. It takes so many hours of running and trial and errors with the coding. So it took a lot of time. And the data set itself is huge, like 1 terabyte to get all those data. So I try to pin down with the whole, economy to specific industry. Generally in trade field, we have issue with curse of dimensionality because we're using all different countries. For example, 200 countries, and trading volume can be determined match with the 2 countries bundled with that. So 200 combination of 2 times several, years, like 20 years, 30 years. It's easily huge number itself as coupled of data set. On top of that, we have lots of features to put in the regression model. So the data set itself is a huge amount. So I needed to pin down to using my computing power to get the decent results. But in other words, semiconductors are most innovation intensive trade sector. So technology similarity means a little bit more relative to other industry. Now let's see pipeline overview. So I collect the patent data. So inside of the patent data, there is abstracts. So collecting all the abstracts and the sentences and the words, I, pre-processing with making a small sets. Patent abstracts is 1.27 millions of patents. So data set itself, we're going to see, but we extract patent abstract and using transformer model. Basically, it is called patent BERT, but there is a several version and several different models for that. So especially I'm using all mini LM L6 version 2. That gives me 384 dimension and to pin down 64 batches to run in my machine easily. And I use citation weighted mean pooling. And by doing so, I finally get the country year vectors to calculate technology similarity. And then building up the panel data set finally. After the calculation of technology similarity, and then merged with corresponding gravity data set. So it is coming out from the CPII. And then I apply all different kind of regression model, logistic regression, and the OLS, panel, fixed effect model, PPML, and to see the different issues to deal with that, I use the Heckman value calculated. Here I show you the summary of data sources. So gravity model data is coming up from the CPII. One part is a BASI, CPII gravity. So I need 2 different set of CPII dataset because one is showing the GDP and the distance and some other variables, bilateral trade agreement, and 2 countries are neighboring each other or they are using same languages. All those variables is including CPII gravity. And the gravity dataset is only has a GDP. So we cannot see direct or specific industries trade volume. So I needed to pin down more granular data set, which is CPII BASI. It gives me that each sector's trade volumes. And another primary data set is patent data set, which is coming out from the USPTO, US Patent Trademark Organization. Usually that data is organized with company level, so it is really hard to follow the originality of countries. By doing so, I connected with the USPTO and the Google Patents database. I can build up the patent data. And for robustness check, I'm using EPO DocDB, which is European Patent Organization. So by doing so, I checking the, only using US origin data relative to the European side of it. So that is the primary data set. And then I can figure out the dimensions of data. Bilateral semiconductor flows is about 2 million. Patent records is 1.24 million. In the middle of that, the semiconductor industry, we can reducing down like a whole about 200 countries to 10 to 12 countries of patent data. So whole things are merged is 903 observations of pairs of countries. But if you merge it with the EPO, it's increasing a little bit, like a 1300. And I checked the robustness of trade link, which is the trade is greater than zero. A trade volume is greater than zero, as I set the number 1. And about 22% is zero trade flows in such an year or such an country pairs. As I just explained, the trade link is 1 if a bilateral binary trade in year T. If there is greater than zero trade, the trade link is 1, other than the trade volume or trade flow is equal to 0, then that's 0. So 22% is missing as a zero trade. And then I use the logarithm of trade value. And I used technology similarity. I used the T-1, which is previous years of technology similarity in the regression model, to avoid reverse causality. And we can see the control variable as a GDP of origin, GDP of destination, and distance is all logarithm value. And contigua, it's neighboring country, and common language as a common lang. Colony, colonial ties in history. RTA is trade agreement. Here we can see descriptive statistics of 903 of data points. Technology similarity mean is 0.698. Trade link 0.78. Distance 8.83. GDP of origin 22.23. So for checking orthogonality, technology similarity versus distance, because we want to see that geographical property is impacting or correlate with technology similarity. So here is a Spearman correlation is a negative 0.03. So very minimal. You can say that technology similarity provides independent variation relative to distance. Now let's talk about a little bit of NLP side of technique. So the model itself I used was all mini LM. Using this model, what I achieved was patent abstract from the raw text and the tokenizer. And next, using the BERT encoder, 6 layers, 384 dimensionality, and mean pooling over token embeddings. So finally we get the EJ, which is dimension of 384 for each patent. So patent BERT is main category or classification. But especially in this sentence BERT, mini LM is used for a little bit light, so memory usage is low. And also the original patent BERT is more suitable for classification instead of this kind of similarity calculation. So I adopted sentence BERT, or in other words, patent S-BERT. The model itself is mini LM. Once I had EI from the previous process, and then using citation weighted pooling method, I generate the vector of a country and a specific time. So that is, citation weighted. So as the formula VCT, country and time, is a summation of weight of I and EI, which is generated from the previous process. So WI is a calculator of cite I divided by summation of all the previous citations. So that weights, and then using that and some of it, and generate the each country's specific time vector is generated. And that vector is once generated, similarity measure, cosine, similarity can be calculated with the following formula. So technology similarity, I to j, country I, country j. So inner product of VI and VJ divided by norm of VI and the norm of VJ is the method to get the cosine similarity as technology similarity. So as the value, I found the most value has coming out from the Korea and Japan, and the second best is Japan and US. So highest value is 0.965. So very similar relative to Australia, and Luxembourg is the lowest value, 0.19. So after all, technology similarity is calculated, and then moving to the prediction model. So first thing I want to check is a link prediction. The model itself is formula like that, and then see each one of the different type of regression model inside of gravity regressions. So the formula of basic lines and some control variables are right there. But I used starting from the OLS and the panel fixed effect model, Poisson pseudo maximum likelihood, as well as Heckman two-stage model to check selection bias. To check the cross-validation, I setting the training set from 1996 to 2014 and 2015 to 2020 used as a test set. So there is some kind of historical event, especially in semiconductor industry, 2018 to 2020, trade war between US and China is happening. But in the specific, subset of testing set, I tried to test it. The result doesn't change that much. But future research, I want to testing out DID before and after checking on that specific time period. And I check OUC and all different type of other measures, even though the value slightly different, but implication is pretty much the same with all those measures. So a little bit specific of what type of model is used. I use the main model is ORS gravity. So using log bilateral trade on technology similarity as well as original gravity control variables. And on top of that, using panel fixed effect model. In addition, I adding ear fixed effect and calculation of standard error clustered by country pairs. And I checked with the negative binomial model to handle over dispersion and As we saw the previous slide, link prediction. Logistic regression was performed gravity only relative to adding technology similarity. And then check AUC ROC on 2015 to 2020. And to checking the robustness, I adding all different type of things. And first thing I did was IPC Jeff index. It is before using NLP model. So 1986 IPC class cosine similarity was used to checking out technology similarity. That is basically classification of the code in the patent. So it is not that kind of content of abstract is not used at all to calculate that similarity. But I use patent expert to replace that old method. And I checked with alternative lags. I use technology similarity with time lag just 1, but I also testing out time lag 2, time lag 3 correspondingly. And then I use a Poisson GLM to checking out the Jensen's inequality bias. Once you're using logarithm of variable, you easily can be underestimate the value out of it. So it is testing out that. And other thing is Heckman's two-stage. Because of the criticism of selection bias, because the semiconductor industry itself is very advanced industry and need more advanced technology, skilled workers, and all those patent is necessary to running the business. So the country already developed only involving this industry. So the trade volume can be easily overestimate. So that kind of bias we worried about and criticized. So I used the Heckman two-stage model to see that. So here is the key findings. So each one of the model showing the beta head of technology similarity is a positive and very significant. Key finding continued, validation and prediction side, hypothesis decision rule, beta head is greater than 0, all of them, and significance is even like not 5%, even less than 1%. Pseudo R-square gains almost 14, and AUC improvement is 0.05. And result of link predictions. In addition, we can see the right-hand side of table, link prediction, test results. Gravity only OUC is 0.78, and adding technology similarity 0.83, so 0.05 of improvement. Corresponding accuracy improvement is 0.06, and precision improvement is 0.07. Another key finding, robustness check results. So IPC Jeff similarity, ORS, panel fixed effect, beta het can be shown in the third column. So 4.34, 4.72, 7.42 correspondingly. And Heckman two-stage model, very last of a third column, 10.559. So that's showing you plus 42% versus ORS. So IML significant, which means the selection bias confirmed. So other things we need to note is, as I reported before, IPC Jeff correlation is 0.63. So embedding model choice was valid, and T-1 lag is used. So to avoid reverse causality. And lag sensitivity was test T2 and T3. Beta head is 7.4 something, so very stable. T-1 is valid. Here I can show you some of my code base. So this one is showing that how I can run the embeddings. So model name is here, all mini LM L6, and device as a CPU to running in the local, and the abstract field NA is used to check 7.6% of patent lacking abstracts. And the batch size is a 64. We can see that embedding shape should be 384. So as I noted down there, patents embeddings MPY, the amount is 1.9 gigabyte. Shape is 1.24 million times 384. Here is another code base. So how to calculate the cosine similarity out of the results from the embeddings. So his is a pairwise cosine similarity. As you can see here, dot product of vector 1 and vector 2 and norm of vector and vector 2 is divided by it. So this code base is showing you the how I build panel data merge with the gravity variables. So from the gravity bar C I, or country of origin, bar C J, country of destination, so the trade value of origin and the destination, distance, contigua, common language, culinary, RTA, trade agreement, and GDP of origin, GDP of destination. And append with the year, technology similarity T-1, and trade link is added for this data set to make a full gravity model. This code base is showing you brief idea of how I run the link prediction. So the feature I use, technology similarity lag, and GDPI, GDPJ, and distance. And using this trained and test scaled, and results is correspondingly coming out. Here is the code base of all other models, regression models. So ORS and PPML. Here is the Heckman selection side of the code base. Now let me introduce conclusion of this project. Hypothesis testing. So first, the hypothesis I was expecting was technology is increasing trade volumes. It is strongly supported by all the models I ran, even OLS2, Heckman. So beta head of all those are positive, and p-value is less than 1%, so highly significant. Second hypothesis, text embedding is better than IPC codes, which is a Jeff index. And the correlation is 0.63, but the result itself is huge, improving from the IPC codes or Jeff index relative to using the patent BERTs, the result what I have here. And the third one is a link prediction improvement. So using the prediction power of adding technology similarity, OUC is increased from the 0.78 to 0.83, 5% points increases. So finally, we can suggest some policy. Under this result, we can say that technology decoupling, which is happening from 2018, US and China chip controls or trade wars, reducing trade, and that is going to be direct trade restrictions, but in the long run, technological diversion can be happened. So main takeaway of this project is global semiconductor trade network hugely impacted by technological proximity beyond gravity model tells us. In other words, patent text embeddings provide a new empirical measure for studying technology trade linkage. Thank you.